Okay, so let's start with this. Let t equal root x. Then dt is equal to 1 divided by 2 root x dx, right? But we said t is root x, so this root x right here is a t. Yeah? Okay, so then 2t dt is equal to dx, right? Like that? Okay. Now notice that the limits of integration do not change, because when x is 0, t is 0. And as x goes to infinity, so does t. So we go 0 to infinity, and then root x is t. So t. And then if root x is t, then x is t squared, right? So e to the minus t squared. And we said dx is 2t dt. So a 2 right here, and the t makes that square, and then dt, right? Okay, and now we're going to do integration by parts. Okay, so for integration by parts, let's leave the limits out, and let's leave that to keep a mental note. We'll have to come back to them or bring them back, right? Okay, but otherwise, let's look at the integral of this here, right, without the limit in the 2. And that we could write as t times e to the minus t squared dt. It suits us to see it in this lens. Let this be u in the integration by parts formula, and this dv. Then we know the integral of u dv is uv minus the integral of v du, right? So if this is u, then du is dt, right? And then if this is dv, then v has to be e to the minus t squared divided by minus 2. It's pretty straightforward to see that. So then the right hand side, this here, is going to be equal to, well, uv is going to say u is t, so t, but from that negative 2, I'll take the minus sign, and then divided by 2. And we can put this downstairs with a positive exponent, e to the t squared, like that. Yeah? And then minus, and v has a minus, so plus, right? And then the rest of v, well, a half here, that's that denominator too. And then e to the minus t squared, du is dt, right? So dt. Yeah? Okay, cool. Now we recall that we had a 2 multiplying the integral. That's convenient because I could do that, and I could get rid of this 1/2, right? And also we need to keep in mind the limits of integration. So I'll put the 0 to infinity on here, but in this part I'll use a limit notation, and of course it needs to be evaluated 0 to infinity. Actually, let's not use limit notation, let's just write it like that. Yes, technically I'm saying in an improper integral, you need to rewrite the integral as saying 0 to a limit is a goes to infinity, but yeah, it's all good. Like, we could do it like this. Yeah? Okay, cool. Now, in this first part, right, like if we send this quotient to infinity, then we're going to get 0, because the denominator is going to dominate the numerator. So we have 0, and then minus, this minus is from the evaluation theorem, but there's a minus there. But so plus, and then when we plug in 0, the numerator is 0, and the denominator is not, so we get 0. And then plus, is this guy familiar? So I have a video on the Gaussian integral, and so I'll link that video below this. But yeah, recall that the integral from negative infinity to infinity of e to the minus, let's use t, why not, minus t squared dt, this here, right, is equal to, it's equal to root pi, right? So if that's equal to root pi, notice that this function is even. So I could write 0 here and write twice the integral, right? So then what that means is this integral is root pi divided by 2. Yeah? Wait, that's exactly the integral I have left to finish the job here. So this here I'm saying is root pi over 2. And if you want to see why in the first place negative infinity to infinity of this is equal to root pi, I will link that video on the Gaussian integral below this, yeah? Otherwise, keep watching. Take care.